So you can pretty much ignore that title because it's a little bit of a mouthful. But really what we're going to be talking about today is effective models in materials physics. And so what I mean by effective models is things like what I kind of just showed up here. Oftentimes we'll talk about atoms as these balls that are interacting with some potential, doing MD on it. That's kind of an effective model. Band structure, the famous band structure is an effective model. The spin models that we use to describe magnetism. These are effective models that really emerge out of the physics of electrons, right? A spin is really just an electron of a given spin saying to the electrons of the other spin, don't come near me. And these are really important to understanding materials, right? I mean, this is really the basis of our understanding of materials. And I think if you come up with a good one of these, you usually get a Nobel Prize for it. So people do value it quite a lot. But they have a little bit of an issue, which is that most of them are a little bit ad hoc, right? Most of them came up kind of out of the genius of the person who decided that this was a good model, a good way of thinking about the material. Not all of them, but most of them came that way. And we don't really have, for the most part, we don't really have a good way of saying, okay, well, this model is really the one that applies to this material, right? Usually it's by experience, right? Usually you look at it and you say, okay, well, maybe this will work. Does that give me predictions that the experiment would agree with, right? And so what I wanted to do, this was some years ago, this has been going on for some time now, was try to be systematic about this. So learn how to systematically build interacting quantum models based on the fine-grained, like realistic simulations we can do for first principles, that kind of like similar to what Saurabh was talking about just a little bit ago. And so we've been working on it for a few years. These are the students who are all in very interesting colors right now. But these are students and postdocs who have been really instrumental in this. And there's a funding down there. It would not have been possible without Blue Waters, of course, and also all this help. So I'm going to take you a little bit through. I don't know how many of you guys really are extremely familiar. How many are very, very familiar with quantum mechanics? How do you feel super comfortable with it? Okay, I see even the expert kind of being a little bit unsure. So yeah, quantum mechanics is hard. So I'm going to remind you a little bit of things and about the way that I'm looking at it. And then we're going to talk about effective models as what we're going to do is recast an effective model as a data analysis problem. And it's going to be a data analysis problem of doing quantum simulations of materials. And then we're going to talk a little bit about, if I have time, applications to real materials and showing, yeah, this actually does kind of work. Okay, so let's talk about this. Okay, the state of a system is described by a wave function in quantum mechanics. Instead of being like the position and velocity, it's a wave function. And this wave function has to depend on the positions of all the electrons at a given time, right? So if you're doing electrons. So that's the wave function. The square of it gives you the probability and that it will be at that position. And the expectation values are taken. You have these operators, which I'm not going to get too much into if you're not familiar with them. But you operate on this wave function, and then you take a big integral, right? And the integral is, in principle at least, many-body if you have many electrons, right? So you're already kind of signing up in a many-body system for a very high-dimensional integral there. And that's the kind of basic quantum mechanics. Okay, so the Hamiltonian is what tells you what the wave functions do. So it's an operator. And for electrons and nuclei, it's that thing. And that's kind of the universal Hamiltonian that tells you kind of how everything works, except for things like nuclear physics and that sort of thing. And there's really special wave functions, which are eigenfunctions. There, when you operate with the Hamiltonian on the wave function, you get back the wave function again with some extra thing, some extra number. And if you know the eigenfunctions and their eigenenergies, then you know the dynamics of the system, right? That's one way of knowing kind of how everything works, right? So they're very special functions. They're very important functions to find. Okay, so let's talk about hydrogen 2 and talk about the wave functions of hydrogen 2. And the reason I'm doing that is that, well, in principle, it's many-body, but 2 is the smallest many-body that you can have. And so let's just talk about that. So we have 2 atoms and 2 electrons. The atoms in this picture are these kind of, unfortunately, blue dots here. And what I'm plotting here is we have 2 electrons, so that's very hard to visualize in 2D, it's 6 dimensions. So what I'm doing is I'm fixing one of the electrons. One of them is sitting on this left, right near this left nucleus. And the other one I'm letting scan around. And I'm just plotting the value of the wave function as a function of where that is, okay? And so this wave function is a Hartree-Fock wave function. It's a non-interacting wave function. And you can see that it really just looks like what you might expect for the density of the hydrogen 2 if you're familiar with that. It mostly likes to sit near the 2 nuclei and kind of it diffuses out between them, right? And so that's a balance between potential energy and kinetic energy, and quantum mechanics kinetic energy makes things want to kind of spread out. Okay, so this is actually a really bad wave function for this system. It will only get about half of the binding energy of H2, so it's quite inaccurate. But if you go to a better approximation, this is a Slater-Jastrow wave function in case anybody cares about that, then now it's not factorizable, and now when I scan this electron position around, it tends to avoid the atom where the other electron is at that time, right? So if I fix the other electron, then it tends to avoid that atom, right? And that's correlation, and that ends up making the wave function a lot better. If you put this physics in there, generally you can describe, say, the binding energy of say, H2 pretty well with this sort of thing. So that's the basic physics that we're trying to describe for electrons and materials. And so the issue with this kind of description is that now our wave function, as I was pointing out, is not separable. Right now you can't factorize it into products of different functions, which means that when we're trying to take these expectation values, we have this many-dimensional integral which is inseparable, right? You can't just factorize it out. And since that's the case, what we do is we use Monte Carlo to evaluate that integral. Okay, and so that's the quantum Monte Carlo that I'm using. There's some technicalities and so on that I'm going to skip over, but that's basically the idea there. Okay, and so if you use this technique, and these are the similar techniques actually that they were talking about this morning with the DOE was funding this QMC stuff. If you use this technique, this is actually results from our group. A lot of this was done on Blue Waters, where you can compute the gap that Saurabh was just talking about of different materials. These are actually very challenging materials that even the technique that quite good technique that he was talking about don't do that well on. We actually can do quite well on those. And this is implemented in an open source code that we develop. So the point I'm trying to get across here for you for this first part is that quantum mechanics involves really many-body wave functions. We really want to know the Hamiltonian for the system. And we have this kind of implementation of quantum Monte Carlo, which does seem to, with judicious application of computer time, it's like 1,000 times more expensive than density functional theory. You can actually get quite accurate results for these wave functions. So we can get these many-body wave functions for near ground states. Okay, so that's the ingredient that you need. So now let's go to effective models, right? So we've done this very complicated calculation. We've gotten results which actually agree with the experimental values quite accurately. But then what do we do with that, right? What do we do with that next? And how do we turn that into kind of understanding the material? And the way we're doing that is through effective models. Okay, so you kind of have to think about these things, you kind of have to hold 2 things in your head. You have to think about the detailed calculation, which is where we track where all these electrons are going. You know, those pictures I was just showing you of the H2 molecule where we had the electrons could be at any position at all in our simulation and we were kind of scanning everything. That's the detailed calculation, where we have a wave function, which is just many-dimensional function, and we know the Hamiltonian. And we take expectation values by taking integrals there. So that's what I was just showing you before. Now what we want to do is from that information, from that calculation we just did, we want to make a coarse grain model. And in this coarse grain model, the wave function is now going to be represented as a vector, which is a finite length. And the Hamiltonian is now going to be represented as a matrix. and the expectation values are going to be done by a vector matrix vector product. And you can kind of see the correspondence there if you're familiar with linear algebra. So that's the kind of thing we're going to do. And just to take you through this idea for H2 again, so we had this, we were talking about, oh, well, this electron is sometimes over here on this atom and sometimes over this atom. And so one reduced wave function description you could have is just keeping track of which electron is near which atom, right? Very reduced description. And so there's 4 possibilities. We have 2 electrons, we have 2 atoms. So electron 1 could be at atom 1, or it could be at atom 2. And electron 2 can be at atom 1 or atom 2, and you take the cross of those and you get 4 possibilities. So that's a vector of 4, right? And that's a huge reduction in the amount of numbers you have to keep track of, because in principle here we should be keeping track of a r to the 6, right, grid, right, instead. So if you can do this, this is a huge reduction. Okay, so the problem is, though, we don't know the Hamiltonian in that relation, in that representation. So we want to really find the matrix, the Hamiltonian matrix, that corresponds to that representation. And I'm going to parameterize it as a matrix here. People who are very familiar with second quantization will be like, why aren't you using second quantization? It's because nobody but physicists knows that. But it's equivalent to this. So we have a matrix, and we're going to parameterize this matrix, and there's some physics behind this. The U is representing basically the energy cost for 2 electrons to be sitting on the same atom. And the T is representing that tendency to spread out in quantum mechanics. It's called the kinetic energy. And if you kind of work all that out, you'll see how that works. And actually, if you just do that, so for example, if you compute the expectation value of the energy by just doing this kind of matrix sum, what you'll see is that the U multiplies the double occupancy, and the T basically multiplies something we call hopping, which is really just how spread out the wave function is, right? So T is called a hopping thing. And so the really important and really critical insight that my postdoc Hitesh had, who's now actually a faculty member in Florida, is that we can actually compute both sides, basically all the terms on both sides of this equation, using that detailed real space simulations. And I'm not going to go too much detail how to do that. If you want, I can talk to you all the gory details about it. I figure the problem is that there's the people who would understand it are, anyway, it's too complicated to explain to people who don't know these things too deeply. Anyway, but we can compute both the left-hand side, all the blue stuff, we can basically compute using our wave functions. They're just expectation values on our wave functions. And so that means that we can set up these equations. And if you look at it this way, if I can compute this, and I can compute this, and then I can compute that, if you know linear regression, that should look familiar to you, because it is a linear regression problem, right? So for every wave function, this has to be true, for every single wave function that you're going to describe. And so we have really an algorithm that comes out of this, where we generate wave functions in the space of interest, right? So whatever wave functions we really want to be able to describe with our low energy model, which is usually going to be some low energy manifold, we're going to generate some wave functions in that low energy manifold. And then we'll just evaluate the expectation value of the energy and some descriptors. So for example, double occupancy on that wave function, maybe the amount of hopping you have in that wave function. There's other things like double exchange and so on that you can also compute using quantum Monte Carlo at least. And then what we have to do is set up this linear equation. And really it's just a linear regression problem at this point. And if that sounds a little bit ad hoc to you, that's because I haven't proved that this all works. We have some proofs that we put out in the past year or so that this is actually the right thing to do. And if you do this, then you can reproduce all the eigenfunctions and all the eigenenergies of the original Hamiltonian without actually having solved any of them. And so you know that you will reproduce the dynamics of the system if you do that. Okay, and so just to show you how this works, if you put a chain of hydrogen atoms together, we can make a T and U model. And actually, you would expect that model to work really well when the atoms are quite spread out, because we kind of viewed it as like an electron is around this atom or an electron is around that atom. When you start putting the atoms very close to each other, which one is the electron by? It's not so clear. And so you would expect the model to get worse as you move the atoms closer to each other. And in fact, that does happen. You actually see that when they're far apart, this is 2.25 angstroms, it's a quite good fit. And when they get closer, it gets worse. And that's actually what we would expect. And so that's really good because it's turning around and telling us not just like what the parameter values are, but also how good our parameterization was, right? So we can really decide this model is better than that model. OK, so we've applied this to some real materials. And this is really where Blue Waters comes in, because we have to do these expensive calculations, and we have to do many of them. And so we've done things like, well, this didn't take Blue Waters, but this is an iron selenide molecule. And it sounds simple, right? It's just two atoms. But if you look at the symmetries of the effective Hamiltonian for that molecule, there's 21 symmetry allowed parameters in that effective Hamiltonian. And we used actually machine learning. We used matching pursuit to select the best parameters. And so you can see as you go iteratively through, you can select the next best parameter one by one. And it actually ends up being things that we're used to seeing as physicists in our effective Hamiltonians. It ends up being things like the Hund's coupling and the bonding between the different atoms. And so we've also done work on vanadium oxide. So here took a bit more calculation. This is a spin excitation, which we used our techniques to compute an excitation that they could see in experiment. They have seen it in experiment, which was really nice to see. We're within error bars of the experiment. Now we've really gone out on a limb. This is what we did in the past Blue Waters allocation. We computed spin excitation on this MGTI-204, which hasn't been measured yet. And we're going to publish it and hope that they actually see it. So that will be exciting. So hopefully it will work, but we think it will. And we've also used this kind of technique to think about unconventional superconductivity. That is a long subject that I don't have time to go into detail on, but I will happily talk your ear off about it at lunch or dinner, where we use this technique to try to understand something about classes of models that apply to materials, right? So kind of really on a general scale, like how do you know what type of model applies to a given material? And we use that to come up with a predictor for whether or not a material might be amenable for unconventional superconductivity. And what you really want to look at here is this one, where the green ones all have this is the probability according to our model of being superconductivity in the family. And you can see all the green ones, which are superconductivity, are up here and high. So we have a pretty good rate at predicting, or post-dicting, I would say, superconducting families there. So that looks pretty exciting, too, going forward. And of course, with this, what we're doing is we're doing kind of a high throughput. Actually, this is actually the next Blue Waters proposal. Is we're doing a high throughput search where we're going to look for new materials which might be interesting to explore more detail. So of course, Blue Waters has been very relevant for this. We need to compute these expectation values using Monte Carlo. We can use as many cores as you can give us. That's not a problem. It's kind of ridiculously parallel. But we need to do a lot of it. And I would say that the data is not a lot of data. I mean, it's of the order of gigabytes or so on. But generating the data is quite costly. And so that's very useful. There's some open questions, which I don't have time to talk about. Mostly it's things like, can we make it faster? And the other thing which I'm very interested in talking to machine learning or any sort of data people, or I don't know who to talk to about this, but finding the basis is really hard. And so I would really be interested in people who have some good ideas on that. And that's the end. So thank you very much.